Okay, question 3, part A. Question 3 is a group of children throwing at a dartboard, and we've got a binomial distribution here with 10 throws, and the probability of a child hitting the dartboard being 0.1, so 10% chance. Two assumptions that Peter needs to make to use her model. It's always the same two, and you've got to write it in context, but it's a constant probability, so I'll write this properly in a second, but it's constant probability and each event is independent. Those are your two every time, okay? As soon as they ask for you for assumptions in binomial distributions, and they love to ask for this, those are your two answers. Then you just have to apply a context to the question. So for the probability one, we're going to say that the probability of hitting the dartboard is the same for every throw. And for the events being independent, each outcome is, so each success of hitting the dartboard or failure of hitting the dartboard is independent of any other throw. So if you can answer the question in the context and make sure you're talking about the probability staying the same for each throw and the outcomes being independent of any other throw, then you are absolutely guaranteed 2 easy marks for this question. Okay, for part B, we're calculating the probability that h is greater than or equal to 4. You've got a couple of ways you can do this. You can use the formula, and if you use the formula, you'd have to calculate 0, 1, 2, and 3, and take that off this, because if you remember, the probability that h is greater than or equal to 4 is going to be the same as 1 minus the probability that h is less than or equal to 3. If we're working out the probability that one of these things happens, the things that can't happen is 0, 1, 2, or 3. So we're going to work that out and take it off 1. The reason I would do that is because it's going to be quicker to work out 0, 1, 2, and 3 than 4 to 10. Now, you could do that with the formula. You're probably quicker doing that with your calculators. Now, if you've got a class whiz calculator, you've got a function that will do this for you. That's in option 7, and if you scroll down, you'll get to the binomial CD. That's binomial cumulative distribution. You've got a variable, so you're going to choose option 2. X is 3, that's going to work out 3 or less. N is 10, that's the total. And P is 0.1, that's in the question up at the top here. So we've got N is 10 and P is 0.1. If we press equals on that, that's going to tell us the answer to this, which is 0.9872. So the probability that we want greater than or equal to 4 is 1 minus that number, which is going to be 0.0128. We have to have 3 significant figures. It's not enough to write 0.13. You lose a mark if you do that in your exam. If you're not sure how I've done this, I've done a video, and that is on my YouTube channel. I'll attach it to the this playlist so you can watch it if you haven't seen how to do this on the ClassWiz calculator. It's really, really useful. if you've not got a class quiz calculator, I'd recommend you getting one because it is properly set up to help you with your A-level maths questions. Okay, part C is a little bit strange, quite unusual on the new course. It says that F represents the number of the throw on which the child hits the dartboard for the first time. So this means what's the probability that the child hits the dartboard successfully for the first time on the 5th throw, which means if it's the first time they've hit the dartboard, they must have failed 4 times in a row and then been successful. The probability of failing is going to be 0.9. So this is 0.9 times 0.9 times 0.9 times 0.9, so 0.9 to the power of 4, and then that child is successful. So that's the calculation to work this out. This is not binomial. They've changed it. They've changed the random variable that we're dealing with. It's not h anymore, it's f. So if we type this in, 0.9 to the power of 4 times 0.1, you get 0.06561. Okay, part D then introduces Thomas, and it says Thomas assumes that in this experiment no child will need more than 10 throws to hit the dartboard. So he's making a probability distribution. If you ever see something like this with a formula or an equation, that's a probability distribution. Okay, so that's a table of values. So we're going to have a new table of values. We're going to go from 1 to 10, because remember now this is how many throws the child needs before it hit or until it hits the dartboard for the first time. So it's going to hit the dartboard and stop throwing. I'm calling it N. And it tells us this equation here. This is his model, depending on what N is. So if we work this out for the first go, we've got 0.1. N is 1 on the first go, so 1 here, so that's a 1 here. 1 minus 1 is 0, so 0 times alpha is going to give us just 0 plus 0.01, so we're going to have a 0.01 here. Then we're going to get to the next one, we're going to have 0.01 add, so when N is 2, we're going to have 0.01 add 1 lot of alpha. So when we work, the only thing we can do for that one, I'm going to move my numbers up a little bit because I'm going to run out of space. Probably won't need to do all the numbers because hopefully we'll work out what the pattern is. So when N is 2, we're going to have 0.01 plus 1 lot of alpha. So I'm just going to write 0.01 plus alpha. The third go is going to be 0.01 again plus 2 lots of alpha. Then it's going to be 3 lots of alpha, isn't it? And that's going to keep going until we get to the 10th throw, which is going to be 0.01 plus 9 lots of alpha. Now, we know that these have to add up to 1, so the total needs to be 1. We've got 9 0.01s from 1, 10 0.01s from 1 to 10, and then we've got 1 alpha, and then 2 alphas, 3 alphas, and that's going to carry on 4 alphas, 5 alphas, all the way up to 9 alphas. So if we think about how many alphas we're going to have all together, they're the triangle numbers, or you can work it out on your calculator, but 1 add 2 add 3 add 4 add 5, add 6, add 7, add 8, add 9 will come to 45. You can check that if you want. So we've got 45 alphas there. Adding 10 lots of 0.01, that's going to be 0.1. That needs to come to a total of 1 whole 1. So 45 alphas is going to equal 0.9. Alpha is going to be 0.9 over 45, which is 0.02. So alpha must be 0.02. For part E, it then says use Thomas's model to work out probability that f is equal to 5. That is going to be probability that f is equal to 5. All we need to do is substitute in our 0.02 for alpha here. So that's going to be 0.01 plus 4 lots of 0.02, which is going to be 0.01 plus 0.08, so that's 0.09. Okay, finally, part F asks us to explain how Peter and Thomas's models are different in describing how the probabilities of the targets, how they compare. If you remember, with Peter's model, the child had a 0.1% chance of hitting the target every single time, which means that they had a 0.1% chance of hitting the target the first time, a 0.2% chance, a 0.1% chance of hitting the target the second time, and so on. With Peter's model, the probability, with Thomas's model, sorry, the probabilities change. They change depending on this alpha value, and if you notice or remember that we increase the value of alpha each time, which means the chance of the child hitting the target increases for the number of times they try. So that's the big difference, that with Thomas's model, has the probability of success, the probability of hitting the target as increasing the more times they try, the more goes they have. Whereas Peter's model has the probability the same for every try. So that's the big difference.